This is problem 51 from chapter 17. The pipe has a mass of 800 kilograms and is being towed behind the truck. If the acceleration of the truck is 0.5 meters per second squared, determine the angle theta and the tension in the cable. The coefficient of kinetic friction between the pipe and the ground is 0.1. Now, one thing to be careful of here is they call the acceleration of the truck A sub t, where T is for truck. This is not to be confused with the tangential component of acceleration. So this is the acceleration of the truck. And in this case, the pipe is being towed behind and the pipe is not rolling. So this is slipping without rolling, which is why they give us the kinetic the coefficient for kinetic friction. So we want to find theta, and we want to find the tension in the cable. And we have Newton's second law, which we can use for the x components and the y components, and then we have to decide whether we want to use equation 17.7 or equation 17.10. So we are going to look at the pipe in this problem. The figure for problem 1752 is the same as the figure for problem 1751. So let's just look at this figure here. So I have the pipe, and I'm going to do a free body diagram for the pipe first, and hopefully this will help me figure out what I want to look at here. So there's G. I have a force of gravity which is acting downward. The mass is 800, so this is 800 times 9.81. And this is 7,848 newtons. Okay, then I have the normal force acting upward here. This is point C, so let's call this NC. And I have a force of friction because the pipe is slipping without rolling. This is kinetic friction. Kinetic friction is 0.1. The force of friction is the coefficient times the normal force between the two surfaces. And so I have a force of gravity. I have a frictional force and a normal force from the ground touching the pipe, and I also have the rope which is touching the pipe, and that exerts a force on the pipe, and that's acting like over here. And this is the tension in cable AB. This angle here is 45 degrees. So this angle is 45 degrees, and that the angle that I want to find is theta. And that's this angle here. So that's theta. This is 45 degrees. And maybe it would have looked better. Well, you can see in this picture here that theta is not the same as 45 degrees. Okay, so, well, before I decide whether I'm going to use equation 17.7 or equation 17.10, I can start off by looking at Newton's second law. And I'm going to do that in the x direction. And the sum of the forces in the x direction, when I do the free body diagram for the pipe and apply Newton's second law for the pipe, that would be the mass of the pipe, which is 800, times the acceleration of the pipe, which is the same as the acceleration of the truck. So that would be 800 times 0.5, which is equal to 400. The forces that I have acting on the pipe in the x direction are the cosine component of tension, so that's TAB times cosine of 45 degrees. And I have a force of gravity acting downward here that does not have a component in the horizontal direction. And I have a force of friction which is acting in the negative x direction, so that's minus 0.1 and C, that's equal to 400. I have two unknowns in this equation, so let's just call this equation 1 and move on to the sum of the forces in the y direction, which is 0 because there's no acceleration in the y direction. And in the y direction, I have the sine component of tension, but since cosine of 45 degrees is equal to sine of 45 degrees, it doesn't matter whether I say sine or cosine, so this is TAB sine of 45 degrees minus 7,848 for the force of gravity, which is acting downward, plus NC, which is acting upwards. That's equal to 0. And we can call this equation 2. Between equation 1 and equation 2, I have two unknowns, so I can find both of those. And that will give me the tension, which is one thing I was asked to find. Well, we're looking for the tension, so I could solve this for TAB cosine of 45 degrees and then put that in this equation here, but that would get rid of the tension and keep NC, but let's do it that way anyways. So if I solve this for TAB cosine of 45 degrees, I'd bring the 0.1 NC over to the other side. So that's 400 plus 0.1 NC. And if I solve this for TAB sine of 45 degrees, NC over on the other side, that would be minus NC, and this would be plus 7,848. And then I can do that because TAB sine of 45 degrees is the same as TAB cosine of 45 degrees. And then I can bring this over to the left-hand side, and that would be 1 NC plus 0.1 NC, so that's 1.1 times NC, and bring the 400 over to the other side. So that's 7,848 minus 400, which is 7,448, and then take that and divide it by 1.1. And you get 6,771. Okay, we weren't asked to find that, but now that we have that, we can go back either to equation 1 or equation 2 and figure out what the tension is. Let's use equation 2. And solving that for tension, I have bring this and this over to the other side, just like we did here. That's minus 6,771 plus 7,848, and then divide by sine of 45 degrees. And when we solve this, we should get 1.522 kilonewtons for the tension. All of that I did just using Newton's second law. Now, if I look at the sum of the moments, I should be able to find the angle theta. Now the question is, do I want to sum up the moments about point G, or do I want to sum up the moments about another point? Well, now I know all of my unknown, all of the forces that were unknown, so I know tension and I know the normal force and can find the force of friction. So let's just sum up the moments about point G, and if I do that, sum of the moments about point G is equal to 0 because the pipe is not rolling, so it's just sliding this way and there's no angular acceleration. So, I guess I can just go ahead and do that here. So if I'm summing up the moments about point G, when I look at the normal force and do the moment for the normal force, that gives me 0. For the force of friction, that would cause rotation in the negative direction, so it's minus 0.1 times NC. And what is this distance here? That is 0.4 meters. And then I have tension, and this angle here is 45 degrees, and this angle here, between here and here, is theta. So this angle here would be 45 degrees minus theta. And if I use that to break tension down into components, the component which is acting along this line here would give me 0 when I do the cross product. So it's just the component which is acting this way. So that would be the sine component, sine of 45 minus theta, which would give me something non-zero when I take the cross product. That would give me something positive when I do the cross product. So that's plus TAB, the distance between here and here, that's the radius, which is 0.4. And then it's sine of 45 degrees minus theta, or rather than thinking about that as breaking this down into components, you could say the magnitude of the cross product would be the magnitude of the two forces times the sine of the angle between the two, and the magnitude of the two vectors times the sine of the angle between the two vectors. The vector r is going like this, so the angle between the two is the 45 minus theta. And the sum of the moments is equal to 0. So, and what am I'm solving for theta here. So I can say sine of 45 degrees minus theta is equal to, bring this over to the other side and put in 6771 for NC, so that's on the other side positive 0.1 times 6771 times 0.4, and then divide by TAB, which is 1,522, and divide by 0.4, and then take the inverse sine of both sides. So you have 45 degrees minus theta is equal to the inverse sine of whatever this is here. And I think for that you get 0.4449. And the inverse sine of that is 26.4 degrees. So then if we solve this for theta, bring theta over to this side and then 26.4 over to the other side, and theta is 45 degrees minus 26.4 degrees, which is 18.6 degrees. And that concludes problem 51.